All right. Today we're going to take a look at solving equations, and you've been solving equations for years. So the concept has not changed. The algebra involved has not changed. The only thing that's changed is the kind of equation that we're going to solve. So I did set this up because I know you can pause. You can also set up a sine wave. We're going to start with solving a sine equation. And this concept is identical for all 6 trig ratios. So I'm going to start with sine. We're going to do several with sine before we move on to any of the other functions. So as you're setting up, you'll notice the first thing I did was I mentioned a solution. A goal to solving any equation is to find all the x values which satisfy the equation. Well, in this case, our x values happen to be angles. So we're looking for all the angles that would satisfy the equation. Okay? Now, before we start with solving, giving you an answer and finding all the angles that give you that answer, let's take a look at the sine wave. We've graphed sine. I put in here 2 periods of sine, one on the positive side, one on the negative side. We know that the period of sine is 2 pi, so I have 1 positive period, 1 negative period. Some of you prefer, as do I, to look at the unit circle, so I'm going to set this up, and I'm going to kind of fill this in. And of course, if you need to pause and then kind of get back to where I am, totally fine. I just want to give you an overall visual. Some of you prefer looking at the sine wave that goes forever. Some of you prefer looking at a circle that goes and is nonstop and goes forever in both directions. So I want to visually show you both. And then you can choose which way you like to represent the sine wave. Okay, now we know on the unit circle, so let me put all these points in. This is the point 1, 0, at pi over 2, 0, 1. At pi, this point is represented as negative 1, 0. And at 3 pi over 2, this is 0, negative 1. And we know from the past experience the sine is the y value. So if I graph on the circle and I go positive, we know that this circle never ends, whether I'm going in the positive direction or the negative direction. So when I unwrap the circle, I can actually keep this pattern going. 0, 1, 0, negative 1, 0, 1, then back to 0, negative 1, 0, 1, 0, negative 1, and this will never end. So we know that the sine domain is all real numbers because, or all real angles, because this never ends. Similarly, I could go in the negative direction and continue with negative 1, 0, and then I'm off the screen. But it never ends. Okay? Our maximum and our minimum, the range is between negative 1 and 1, and it just oscillates. So the highest value the sine can ever be is 1. The lowest value sine can ever be is negative 1, unless we amplify it. But right now we're looking at just the sine wave. Okay. Now I also put over here references of 30, 60, 90, 45, 45, 90. And if you recall, 30 degrees, because that's the one I'm going to take a look at first. Oh, hey. 30 degrees is 180 divided by 6, pi over 6. Okay. So depending on how you look at the sine, again, some of you prefer looking at the wave. Others prefer looking at the unit circle. The approach won't matter. What matters is knowing where the sine value, sine is positive or negative. So if you're looking at the sine wave, our outcome outcome is positive between 0 and pi. So it goes positive and it's positive, and then the sign values go negative and stay negative for the period. If you prefer the unit circle approach, we know that all students take classes, so we know that sign in this first quadrant is positive, sign in this second quadrant is positive, then sign goes negative, negative. Same thing we had here. Positive, these are still above 0, so they're positive. Both of these are below 0, so they're negative and negative. Positive, positive, negative, negative. So again, doesn't matter. So here's our goal. Our goal is to solve for x. And we know the period is between 0 and 2 pi. Now, just for a visual, let's see if I can find a couple of pieces of paper. We know the sine wave is between 0 and 2 pi. So if I copy and I slide it and I paste it, it's now between 2 pi and 4 pi. So I've added 1 revolution. If I do this again, I would add 2 revolutions. So again, 0 to 2 pi is if I add nothing. This is the original graph. 0 to 2 pi has no extra periods added in. But then if I add another period, it would go all the way to here, to 4 pi. If I add another period, it would keep going to 6 pi. So keep that in mind as we get going. So here's our first example. And I know it took a while to get situated, but I wanted to make sure everybody had a visual. I would like to solve sine of x equals 1/2. So I've now told you what the y value is. I've told you the y value. The answer is 1/2. So I'm going to go through this one kind of slowly. And I'm going to write all over this. So we want the output now to be 1/2. Okay, well 1/2 is halfway between, obviously, 0 and 1. So what I'm asking you to do is I would like you to solve. I would like you to find every single x value that gives an output of 1/2. So I need to find the x value for this point. I need you to find the x value for this point. I need you to find the angle or the x value for here, the angle that gives me this output, this output, this output, forever and ever and always. In addition, I could go in the negative direction. So first of all, if I asked you to solve and find all of them, there are an infinite number of solutions because I have an infinite number of outputs that are going to be 1/2 on the sine wave. Okay? If I look at it in terms of one period between 0 and 2 pi, now let's just look at that. Between 0 and 2 pi, how many places, how many points have an output of positive 1/2? Well, I only have 2 of them. I have a positive 1/2 right here, and I have a positive 1/2 right here for the y value. So how many solutions do I have within one period? 2. Now, what if I add in another period? Well, if I slide this over and I add another period, notice I get 2 more solutions. They happen to be located in the same relationship. So it looks like they're located in the first 2 quadrants here between 0 and pi. And if I add in a 2 pi, notice they're in the same location in the first of these 2 quadrants that I have representing a period of sine. Okay, so it looks like if I can find them in the first period, all I have to do is add a period, or all I have to do is subtract a period, and I get all the solutions. So our goal, let's start with finding all the answers that are in the first period or one period of sine. That's my goal. So I'm going to leave that right here on purpose. Our goal is to find these two angles. Now, some of you don't like working with the sine wave. You prefer working with the unit circle. So I'm going to do the same thing. I'm looking for an outcome that's positive. So I know in the unit circle that sine is positive in the first quadrant and the second quadrant. So therefore, I'm going to look for numbers that are in the first and second quadrant. Since we want an output of 1/2, this is the same as the opposite value and the hypotenuse. Here it is, you guys. Don't make it more difficult than it is. I'm going to create an angle into the first quadrant, because that's where sine's positive. I'm going to create this central angle. I called it x this time. Okay? And I know the opposite side is 1. I know the hypotenuse is 2. So therefore, it's automatically a 30, 60, 90 degree triangle. So right here in the quadrant 1, and I'm going to put that up there, right here in the first quadrant, our angle is 30 degrees. Okay? So right here in the first quadrant, our angle x is 30 degrees. Now I'm going to come back and make this look more academic. I'm going to raise it up in just a moment. Where else is sine positive? Well, sine is also positive in the second quadrant. If you prefer the graph, sine is also positive between pi over 2 and pi. Between pi over 2 and pi. So if I put my other angle that goes into the second quadrant, I'll put it in green, This has to go all the way into the second quadrant. So I can clearly see that it's got to be bigger than 90, but it's less than 180. So if you remember, we have to use this reference angle. We always refer to the horizon. We always refer to that acute angle. So again, the opposite is 1. The hypotenuse is 2. That makes sense, because if the radius of the circle is 2 here, the radius of the circle is going to be 2 everywhere. And this is square root of 3. So again, this is a 30-degree reference angle, but that's not what I'm interested in. I'm interested in that obtuse angle that provided and created a 30-degree reference angle. So since this is 180, 180 less 30, in quadrant 2, it would be 180 less 30. So x equals 150 degrees. That's the hardest part of solving it, in my professional opinion. The hardest part is creating the triangle that's in the quadrant. Okay? This is off the screen. I apologize. This says 180 minus the 30-degree reference angle. That's how we got the 150. All right, so that's the algebra way of writing the problem. So I'm now going to do the same problem using math analysis, pre-calculus. Okay, instead of saying sine x, we know that what we're solving for are all of these pi over 2, pi, 3 pi over 2, all these angles. So I'm going to write this sine theta. Okay, so we now figured theta in the first quadrant is 30 degrees. Well, we know how to change 30 degrees into radians. It's got to be 180 pi. So I end up with this angle being, if I reduce pi over 6, or 180 degrees divided by 6 is 130. So we would write this as 1 pi over 6. I can do the same thing with my 150 degree angle. My 150 degree angle, well, if I multiply this, do I have room? I do not. If I take 150 degrees and multiply it by pi over 180, reduced by 10, divide by 3, I get theta equals 5 pi over 6. And there's another way to calculate, but I'll do that a little bit later. Let's just start with what we know. Okay, so that's all the answers, either using the wave or the unit circle. All the answers to get positive 1/2 in one period. But I don't want the answers in just one period. I want all the answers. So what do? Well, if I look at the wave, remember I had to add another period of sine. I had to add a second period. Then I add another period of sine, and then I add another one. Or, here's one period of sine. I subtract one period. So you can use this on the sine wave. You can also do this on the unit circle. If I start with my answer right here in the first quadrant, well, if I add 2 pi, I get right back to the point that is coterminal in the first quadrant. If I add 2 revolutions, or 2 pi's, I land coterminal in the first quadrant. I could start here and add 1, 2, 3 periods and land in the same spot. Or I could subtract 1 period and land in the same spot, or subtract 2 periods. I think you have the idea. So to get all the solutions, you guys, it's this simple. Start with the one original and then add 2 times however many. Let me rephrase that. Add in k times however many periods we need. If k is 0, we just found our original answer. But if k is 1, we start with our original answer and add 1 times 2 pi. If k is 2, to represent 2 periods, we would go once, 2 times 2 pi, etc., etc., etc. So since the period of sine is 2 pi, to get all of our solutions, we start with the original, and then we add in however many periods we want. So we call that 2 times k pi. 2k pi. And that represents every single solution that will be 1/2 for the sine wave. So if you want them all, there they are. There they are. Okay? So I want to do this again with cosine. It'll go a little quicker because we now have the concept. All right, so I'm going to do this again. I'm going to pause for a moment. I'm going to set up the cosine wave, and I'm going to set up the cosine on the unit circle. So you might do the same. So I'm going to pause. I'll be right back. Okay, now we're back. What I did was I set up the cosine wave the same way so that we can analyze it, but it'll go a little quicker this time because you have the overall concept. Again, if you prefer one period of cosine on the cosine wave, you'll notice that the entire cycle happens between 0 and 2 pi. If you prefer the unit circle approach, the unit circle says cosine is your x values, so we get 1 0, -1, 0, and we finish this cycle or the period or the circle back at 1. So here's one complete revolution, one complete period of the cosine wave. Again, cosine. In the first quadrant, all 6 of them are positive, and then cosine goes negative, cosine is still negative, and then cosine finishes the period being positive. So cosine, right, now some of you prefer, let's see, all students take classes, yep. So cosine is positive, negative, negative, positive. Okay, so we always need to keep that at the back of our mind. Whether you prefer the cosine wave or the unit circle doesn't matter. Now with the same idea, cosine, because circles are non-ending, the cosine wave is non-ending. So I'm going to continue this out so that we can get a visual. So cosine would continue this pattern. Now notice I've counted 1 pi over 2, 2 pi over 2s, 3 pi over 2s, 4 pi over 2, well 4 over 2 is 2, 5 pi over 2, 6 over 2 is 3, 7 over 2, 8 over 2, 9 over 2. Oh, I guess I could have finished 10 over 2. And if I keep this cycle going, I go 1, 0, -1, 0, 1, 0, -1, 0, and this would have kept going had I kept the pattern up. Similarly, I could go the circle the other way. So it goes 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, etc. So we know this from prior experience that it's never ending. Okay, the domain is all real angles. All right, so I'm going to do a similar one just to keep the idea going. Let's solve y equals, oh, not y equals, sorry, here's y equals. Let's do, let's solve cosine of some angle theta, and I always like to put it in parentheses. You'll see why in a little bit, but I always like that in parentheses. Equals, again, let's do positive 1/2. Trying to keep it simple without radicals the first time through. Same idea. We want to find where on the cosine wave, we want to find all the places the graph hits 1/2. Well, it sure looks like it hits 1/2 here. Positive 1/2, positive 1/2, positive 1/2, positive 1/2. So you can see that once again, we have an infinite number of solutions. Every single time y equals 1/2. And we know y is a horizontal line. So again, I'm just sort of giving you a visual of all the places that horizontal line of y is 1/2. Our job is to find all the x values, rather all the input or the domain, the theta values. So this is a little close because my graph's not perfect, but it looks like it happens in the first quadrant, not the second quadrant, not the third quadrant, but it looks like it happens again in the fourth quadrant. So within one period of cosine, it looks like we have 2 solutions. Okay, so I'm going to do that on the unit circle. Because we're looking for a positive 1/2, and cosine is positive in the first quadrant, let's figure out what our angle is in the first quadrant. Cosine's positive. Okay, I'm going to go into the first quadrant. I'm going to call this angle theta. Because it's in a quadrant, I'm going to make a right triangle out of it. Cosine is adjacent over hypotenuse, which means our adjacent side is 1, our radius of our circle, our hypotenuse is 2. So this time it's across from the square root of 3. Well, according to our right triangles that are special, the angle that's across from root 3 is 60 degrees. So it looks like that angle is 60 degrees. Okay, but it's better to write it in terms of radians. So 60 is the same as 180 divided by 3. Now let's do the same thing on the other version. Again, it was positive 1/2 in the first quadrant. And it's also positive 1/2 between 3 pi over 2 and 2 pi. According to this, it's also positive in the fourth quadrant. So here I'll switch colors. I'm going to come all the way around to the fourth quadrant, but I don't use that large angle. Instead, I use and refer to this other angle. And again, same circle, same radius. If the adjacent side is 1 and the hypotenuse is 2, this other side again always be the same. The reference angle is identical. So for those of you that are following along, once you find the reference angle once, it's going to be exactly the same in every quadrant. So our reference angle is still 60. Since it's in the fourth quadrant, I have to come all the way around past 270 degrees. I've almost made it to 360. So I take my, how much room do I have? I take my 360 and I subtract out that same reference angle. It's always going to be the same. So once you find it in the first quadrant, it's always going to be the same no matter which quadrant we're talking about. So again, now here's the cool part. If I know it's pi over 3, okay, then I would know that this is 3 over 3, because that's 1 pi, 3/3 of a pi, which means 2 pi is the same as 6 over 3. So I'm going to take 6 over 3, and I'm going to subtract 1 over 3. So I'm going to take 6 pi over 3, and I'm going to subtract my 1 pi over 3. And so that angle becomes 5 pi over 3. There it is. There it is. I just drew a picture for the first and the fourth quadrants. That's it. Now let's find all the answers. So how do I find the set of answers if I add a period? How do I find the next set of answers if I add another period? Since the period is 2 pi, I add 2 pi times k, where k represents the number of extra revolutions. So this answer would be pi over 3, which landed in the first quadrant, plus however many 2 pi's I'm going to keep adding. So we call that 2k pi. And that's it. There's our solutions. So the exact same procedure happens with tangent, secant, cosecant, cotangent. Okay? Only with tangent, we get 1 pi. So I'm going to do a tangent, and then we're going to practice a few more. Okay? Then I'll probably do a second video that is just solving more problems for practice. All right. Before I do tangent, let's do another sine or cosine. Before I do tangent, since we have the idea here. Okay. So we now have the goal. We're looking for all the answers. Now sometimes they will restrict us. They don't want all the answers. But sometimes they do. So here we go. I'm actually going to start with, we already did 35. I'm going to do number 40 to start with. It says, solve the equation and give a general formula. Solve and then give a general formula. Then it says find 6 solutions. Okay. So we want to solve sine theta equals root 2 over 2. So you have a choice. You can use the sine wave. You can use the unit circle. I'm going to look at the unit circle. Okay? So I'm going to look at sine. On the unit circle, sine is positive. All students take classes. Sine is positive in the first and the second quadrant. So sine is positive between 0 and pi over 2, and between pi over 2 and pi. So I don't even need to worry about the other two quadrants because I'm looking for a positive output. Now, root 2 over 2. Well, that is not one of our quadrant angles because sine goes from 0 to 1 to 0. So that must mean it lies inside the quadrant. Okay? Now, if it lies inside the quadrant, for this year, we're only using our special triangles. So let's think about our special triangles. If we have a 30, 60, 90, we know the ratios have a 1, a 2, and a root 3. Well, there's no square root of 2 in there. If we look at our other special triangle, 45, 45, 90, we have a 1, and a root 2. There it is. It's got to come from that triangle because there's a square root of 2 in it. So sine of 45 is 1 over root 2. Okay, and I'm just refreshing your memory. Sine of 45 is 1 over root 2, but you're not allowed to have a radical in the denominator. So back in the days of algebra, we would have rationalized it, and notice what we would have come up with. Okay, so what we have is, there's really no such term, but I'm going to unrationalize this. That's not really an answer. It's not really a word, but my answer is root 2 over 2. So I'm going to go back to 1 over root 2, and then that'll tell me what angle it is. So now I know the opposite is 1, and the hypotenuse is root 2. So I am looking at a 45-degree angle. So here's what I do. I go, okay, I've now figured out that it's a 45-degree angle. I now know this is a positive fraction, so sine has to be in the first or the second quadrant. So honest to gosh, this is what I do. I go, okay, in quadrant 1, well, we already figured it out. Theta has to be, we already figured it out, has to be this 45-degree angle because it's a 1 to root 2. Okay, so we've got that one. In the first quadrant, sine is 45 degrees. Oh, wait a second. Better written as 180 divided by 4. But we also said sine was positive in the second quadrant. Now remember, we already have the reference angle. So in quadrant 2, it's got to come all the way around past 90 and land in the second quadrant. Now guys, we already have the reference angle. We already know that this angle is 45. We already know it. So let's see. That's pi over 4. So this would be 4 over 4 because that's the same as 1 pi. So I'm using the same denominator. So in the second quadrant, it is, I'll first do it, it is 180 minus the 45 degrees, so I could say 135, but I'm trying to shy away from that. Or I could say it's 180 degrees minus pi over 4. Remember, I wanted the denominator the same, so I just made that 1 pi into a 4 over 4. And so that gives us 3 pi over 4. So it's the same process we just did. Okay, so look at the directions. It says solve. Okay, we found the first two that are in the first period of sine. Give a general formula. General formula, okay. Theta equals pi over 4 plus 2k pi. Since the period's 2 pi, I'm just going to add in as many extra periods as I need. K can be 1, K can be 2, K can be 3. That just represents another cycle. Our general formula here, theta equals 3 pi over 4. Again, the period is still 2 pi, so I'm going to add in k numbers of 2 pi. All right, so I've solved it. I found the general formula. Now it says find 6 solutions. So here we go. Let k equal 0. That means if k is no extra revolutions, I want the original 2 answers. Okay, so our solution would be pi over 4, 3 pi over 4. Whoops, hold on. Did not mean to put a set there. This represents when k was nothing. Now let's add in 1 extra rotation. So let's let k equal 1 extra period. All right, I should have left more space. I apologize, I'll do it on the next one. We'll do this mentally. If k is 1, that's 2 pi's plus 1/4. So that's 2 1/4, or add in 4 over 4. Okay, add in 8 over 4. I better do it over here. I apologize, I should have left room. My mistake, I just didn't plan well. So I'll do it over here. So if k is 1, that means this would be pi over 4 plus 2 times 1 is 1, so 2 pi. But I'm going to write this using a common denominator. 2 is the same as 8 over 4. So 8 over 4 plus 1 over 4 gives me 9 over 4. If k is 1 for the other version, same idea. I'm going to get 3 over 4 plus 2 pi. So I need a common denominator. Well, that would be 8 over 4, because 2 times 4 is 8. So now 8 over 4 plus 3 over 4 gives me an answer of 11 pi over 4. That's if I add 1 extra period. Now let's do it again, because it said to find 6 solutions. So I have 1, 2, 3, 4. It looks like I need another set of solutions. So what do? This was the original period where we didn't add anything. Here I added in 1 extra period. So now I'm going to add in another period. So if k is 2, substitute it in. pi over 4 plus, now I need 2 times 2 pi. So I'm adding 4 pi. Again, you all know you have to add common denominators. So here's pi over 4 plus, I need a common denominator of 4, so that becomes 16 over 4. So I end up with 17 pi over 4. Let k equal 2. So I'm taking my formula, I'm taking our general formula, 3 pi over 4, again 2 times 2, and this will go faster because you'll start seeing the patterns that show up. So theta equals 3 pi over 4 plus 4 pi, well we just did that, so that's the same as 3 pi over 4 plus 16 over 4. And so we end up with 19 pi over 4. So if I add in 1 extra period, 2 extra periods, here are my 2 answers. So you may see a pattern, okay? And so now we have 2, 4, 6 answers. We've satisfied that. And there's how we can find the general equation and all 6 solutions, okay? So that helps you with that 35 to 44. Okay. All right, so that's kind of the general idea. Now I'm going to go ahead and walk through actually I'm going to pause this one, then I'm going to start a second video where I do tangent and I practice more problems. So that's a good introduction. That'll get you started on your homework, but I'm going to keep going in a second video, so if you want to keep going right now, that's fine. Or you can pause, kind of get this in. This will help you for sure. This will help you to practice problem 7.3, the section that is 35 to 44, whatever your homework was in that section, but this will help you set it up. So I'm going to pause here and then I'll start with a second continuation video.